Hi, today we will discuss modeling of structural systems. From the actual structures, we would like to idealize it for structural analysis. For an overview, I will give you some real structures and then see the modeling skill, then the support connections, idealize models, idealize structure, and the concept of tributary loadings. Here you will notice the deck of a concrete bridge is made so that one section can be considered roller supported on the other section. See, it's not directly at the support, but you will see it here, this portion. This is similar to this building. Uh, it has also a simply supported connection. This one, if pin connected steel members, as you can see, the eye sections are connected with bolts. A real structural system is so complex that exact analysis of the structure can never be carried out. And since estimates always have to be made of the loadings and the strength of the materials composing the structures, also the points of application for the loading must also be estimated. So, as a structural engineer, we need to develop the ability to model or idealize a structure to perform a practical force analysis of the member. Structural members are joined together in various ways depending on the intent of the designer. And there are three types of joints which are mostly used in our structures. First is the pin connection, second roller connection, and the third one a fixed joint. A pin connected joint and a roller support allow some freedom for slight rotation, while a fixed joint allows no relative rotation between the connected members and is consequently more expensive to fabricate. Here are examples for different joints. First, for the metal joints, as you can see, there is the angle connection with bolts on this one. This is a typical pin supported connection for metals. This is the side view and this is the cross section. The other diagram is a fixed supported connection for metals. Aside from the angle connection that you can see here with the bolts, there is an added welding at the top plans and the bottom plans. Also with another support here, an angle connection with the bolts. And aside from that, the stiffeners are added along the line of the top plans and the bottom plans. This will make the connection moment resistant. So it will hold moment. For the concrete joints, the first diagram is a typical roller supported connection for concrete, and the other one is a typical pick supported connection for concrete. As you can see, we have the reinforcement for the columns and for the beams. So the beam is uh, rigidly connected to the column. Also, aside from the metal and concrete joints, most timber structures, the members are assumed to be pin connected since bolting and nailing them will not sufficiently restrain them from rotating with respect to each other. For the idealized models of supports and joints, the idealized model for supports and joints can be pin and pig support, also pin connected and fixed connection joints. So here are again an example of these supports and joints. The first diagram, the triangular one with circular uh, point and a stick model. This is what we call a pin support. For two members connected with a circle, this is we call pin connected joint. We allow rotation for this joint. While for the fixed support, as you can see here, the stick model is connected to a fixed, a rigid support. So this is a fixed support. While the connection between or the joints between the two uh, members, a structural stick or a stick model, as you can see, it's not a circular diagram, but a jumper at this corner. This is a fixed connected joint. In reality, all connections exhibit some stiffness toward joint rotation, owing to friction and material behavior. So in this case, a more appropriate model for a support or joint might be like below. If the torsional spring constant is equal to 0, that is K is equal to 0, then the joint is a pin joint. So you can see here the first diagram, the torsional spring support with K is equal to 0. It is a pin. And if K is reaches infinity, the joint will become fixed, this one. If you have K infinity, then the joint for these two members will be fixed. For the modeling assumptions of support, here we selected a particular model for its support or joint. The engineer must be aware of how the assumptions will affect the actual performance of the member and whether the assumptions are reasonable for the structural design. For example, we would like to consider the beam below, which is used to support the concentrated load P. The angle connection at support A is like a typical pin supported connection for metal. So you can see this is the diagram. This is a typical pin connected or pin supported connection for metals. So in our example, uh, the support A is idealized as a typical pin support. The support at point B here provides an approximate point of smooth contact, and so it is idealized as a roller. So we have a hence or a pin support and a roller support. Take note the beam's thickness can be neglected since it is small in comparison to the beam's length. If you have to apply some loading for the uh, beam, here we have the concentrated load P, so we also copy the concentrated load P, and the beam can be idealized as a stick model, and as we mentioned earlier, support A is a pin support, support B is a roller support. So here is the idealized beam for our actual beam on the left. So as you can see, if you have to apply some quantities for P, like for example, uh, this will result to some rotations, although the rotation is quite small, which is tolerable for the beams that we are analyzing. For more types of connections, it is important to be able to recognize the symbols for these connections and the kinds of reaction they exert on their attached members, so that when we are modeling for structures, as soon as we will know the connections and reactions, we can just use the symbols as presented. This can be easily done by noting how the connection prevents any degree of freedom or displacement of the member. In particular, the support will develop a force on the member if it prevents translation of the member. So remember, the support will develop a force on the member if it prevents translation of the member. So kung horizontal, if it will prevent the translation horizontally, then there will be a, a force that will act on that. Also, if it will prevent vertically, then there will be a reaction vertically. Of course, it will also develop a moment if it prevents rotation of the member. So in that way, if the support will prevent movement horizontally, vertically, and a rotation, then there will be 3 degrees of freedom. Note that in reality, all supports actually exert distributed surface loads on their contacting members. the concentrated forces and moments represent the resultants of this load distribution. So although in reality it's not really concentrated load, but we can usually represent that uh, distributed load as a single force. That is what we call the resultant. This representation is of course an idealization. However, it is used here since the surface area over which the distributed load acts is considerably smaller than the total surface area of the connecting members. So here is a table from Heveler, table 2.1 for the supports for coplanar structures. As you can see, there are four columns: the type of connection, then the idealized symbol of the connection, and the reaction, and the number of anons. Like for example, for type 1 connection, we have a light cable with oriented at an angle theta from the horizontal. So with the weightless length, which is also uh, oriented at an angle theta with the horizontal. This type of connection can be idealized like this one. So as you can see, there is the circles, which means the pin connection. Uh, and the reaction for that is this one force only that follows the path of the light cable or the length. This one anon or the reaction is a force that acts in the direction of the cable or length. This one follows the length and the cable. Aside from that, we have rollers. So as you can see, the actual connection is something like this with different rollers at the bottom, or with only one roller. This is the cylindrical steel put under the uh, structure. Also, aside from uh, the rollers will be idealized like this one. So the first roller can be idealized as a triangle with circular rollers at the bottom, and then the pin connection, and then a stick model. And for the other type of model, we only have a circular one, and then the stick model. Unlike the rocker, as you can see, this is the the actual dimension or the actual structure, I mean, and then the idealized symbol will be like this one, just like a rocker. Now, the force for a roller or a rocker is just one. There is one anon. This reaction is a force that acts perpendicular to the surface at the point of contact. Remember, it should be perpendicular to the surface of the point of contact. Here, the diagram, the surface are all horizontal. So that's why the reaction is perpendicular to the horizontal, which is vertical. But if your surfaces are inclined, then the reaction force should be perpendicular to the inclined surface. Another type of connection is a smooth contacting surface. So here, and we only have one anon, one reaction. The reaction is a force that acts perpendicular to the surface at the point of contact. Again, it should be perpendicular to the surface of the point of contact. So if your point of contact or the surface is inclined, then it should be perpendicular to the inclined surface. The fourth connection is a smooth pin connected collar. It can be idealized like this one. You will draw a cylinder, and then with the length as a stick model. Again, we only have one unknown for this one, which is perpendicular to the surface at the point of contact. The other one is a smooth pin or hands. Look at this one. This is uh, oriented at an angle theta with respect to the horizontal. So the idealized symbol will also be like this one, a triangle with circle, and then the stick model with the angle theta. For this particular type of connection, a hands or a smooth pin, there will be two anons. normally the horizontal and the vertical, or in terms of the axis, the x and y axis, we have the component along the x-axis fx and the component along the y-axis fy. Also, we have the slider with the corresponding idealized symbol and the fixed connected color. The These types of connection will have two unknowns. The reaction will be a force perpendicular to the member and a bending moment. The last one is the fixed support. This will be idealized like this one with a stick model and then a fixed support. The fixed support will have three unknowns. The force in the x-axis, that is Fx, the force along the Fy, along the y-axis, that's Fy. Remember, the x and y-axis should be perpendicular to each other. So this reaction should be perpendicular to each other to be independent. Aside from that, there will be a moment. So for a fixed support, we have three unknowns. The reactions are two forces and one moment. Here is an actual structure. The first one is a typical rocker support, which is used for a bridge girder. And the next picture is a concrete smooth or roller support. It is si tawag ni nakapatong man ni siya. Oh, nakapatong lagi sa concrete nga column. Also, we have a short length which is used to connect the two girders of the highway bridge and allow for thermal expansion of the deck. The lower picture is rollers and associated bearing pads which are used to support the pre-stressed concrete girders and highway bridge. Some of the bridges nowadays, we don't use these directly rollers, but we use the bearing pads, the rubber bearing pads, elastomeric pads. Ang ibutang diri mo siya o flat lang, rectangular, sapaw-sapaw siya, and that will be idealized also as a roller. Also, we have the steel pin support here, the last picture. So now we can now idealize structure. This is a jeep crane and a trolley. If we consider this type of structure, uh, for the structural analysis, we can neglect the thickness of the two main members and will assume that the joint at point B here, the joint at B is fabricated to be rigid. So as you can see, there are angle connections at this corner. So we can assume this to be rigid. Furthermore, the support connection at point A can be modeled also as a fixed support. As you can see, again, there are angle connections at the two flange sections of the steel. Mm. And the details, of course, of the trolley can be excluded as of now. So thus the members of the idealized structure are represented by two connected lines. This is the cantilever frame, which we have a stick model from support A to point B and B to this portion. But take note that at joint B, it is drawn to be a rigid connection. Aside from that, we have added the concentrated force F at this portion. How about a typical floor slab? In this diagram, we can idealize this as a pin and roller connected. If we can consider this framing is used to support a typical floor slab in a building, and this slab is supported by floor joists. As you can see, mura siya og truss ang mga joists. This is what we call a floor joist. Of course, the floor joists are usually uh, located at even intervals, and these in turn are supported by the two side beams. We call it girder because this is a larger beam. Of course, joist is also a beam. So a joist is usually supported by a larger beam. We call it the girder. We have the girder AB and girder CD. For analysis, it is reasonable to assume that the joints are pin and or roller connected to the girders, and that the girders are also pin and or roller connected to the columns. The top view of the structural framing plan for this system can be shown on the right hand picture. As you can see, we have the columns, the I-beam, so it is also represented as I, and the girders are connected to the columns here, and the joists are connected to the girders. If you notice, there is a gap between the joist and the girder and the column. Uh, in that graphic scheme, we usually represent the joist to not really touch the girder and the lines for the girder to not touch the columns. This is to symbolize pin and or roller supported connection. So if you have seen a picture like this, or actually if you have seen this one in a plan, then it represents this to be pin and roller supported connections. On the other hand, if the framing plan is intended to represent fixed connected members, such as those that are welded, instead of simple bolted connections, then the lines for the beams or girders would touch the column. So as shown in the figures below. So as you can see, for a fixed connected beam, this one, since this is fixed connected, then the idealized beam, you will have the column, the I column, and then you can connect the idealized beam. So there will be no further gap between the column and the beam because we represent this to be rigidly connected. Aside from that, we can have fixed connected overhanging beam uh, representing this diagram. So as you can see, the cantilever portion is also connected to the column. For the reinforced concrete, usually this is fixed connected members. So if the beams and girders are usually represented by double lines. These systems are generally all fixed connected and therefore the members are drawn to the supports. For our example, the structural graphic for the cast-in-place reinforced concrete system, as shown in the top view, and the lines for the beams are dashed because they are below the slab. So as you can see, there are two girders supporting the uh, slab at the top. For a timber and masonry structure, structural graphics and idealization for timber structures are similar to those made of metal. For example, the structural system below, this represents a beam wall connection whereby the roof deck is supported by wood joists which deliver the load to a masonry wall. The joist can be assumed to be simply supported on the wall so that the idealized framing plan would be like that on the right hand side figure. Also for concrete floor joists and girder, taken as is simply supported. Uh, as you can see, the structural framework of this building is consists of a concrete floor joists which are formed on site using metal pans. These joints are simply supported on the girders, as you can see, which in turn are simply supported on the columns. Also, there is what we call the one-way system. A slab or deck that is supported such that it delivers its loads to the supporting members by one-way action. That is referred to as one-way slab, meaning the forces will be transferred only in one direction. So that's one-way action. To illustrate the method of load transmission, we can consider the framing system below, where the beams EB, this one, CD, and EF rest on the girder AE and BF. As you can see here in the plan, that is AB and BF. What will you do Normally, we actually use a tributary area for this particular model. The tributary area in this case is the shaded portion. How do we determine the tributary area? First, we need to determine the dimensions. So normally, we have to take half the distance between the beams. Beam AB and beam CD has a distance of 5 meters. Take half of it so that it will become 2.5 and 2.5. On the other side, it is also 5 feet. You have to take half of it, 2.5 and 2.5. So half of it will be taken from here and the other half will be taken from here. So this portion, this is what we call the tributary width times the length of the beam. So the shaded portion is what we call the tributary area. Normally, to determine the load applied to a particular beam, like beam CD, we will just multiply the force or the uniformly distributed load, in this case 100 pounds per square foot, to the tributary width, which is equal to 5. So 100 pounds per foot square times 5 feet will become 500 pounds per foot. So this is the result, which is a uniformly distributed load. If we take the reaction for this, 500 pounds per foot times 10 foot or 10 feet, we have 5,000 divided by 2, that's 2,500 pounds. So here is 2,500 pounds and 2,500 pounds. And if we have to transfer this one to the girder, like girder AE or BF, in this case, the reaction of uh, CD will be transferred to the midspan of AE. Here we have 2,500 pounds, and also the reaction from beam AB is 1,250 pounds and EF to be 1,250 pounds. So this is how we idealize the structure from the slab to the beams and girders towards the column. Here is an example of a one-way construction. An example of one-way slab construction of a steel frame building having a poured concrete floor on a corrugated metal deck. The load on the floor is considered to be transmitted to the beams, not to the girders. For some floor systems, the beams and girders are connected to the columns at the same elevation, as you can see in the figure below, because this is easier and this is more advantageous also for the floor-to-floor distances. If this is the case, the slab can in some cases to be considered a one-way slab. For example, if the slab is reinforced concrete with reinforcement in only one direction, or the concrete is poured on a corrugated metal deck, as in the picture below, then one-way action of load transmission can be assumed. So for this particular actual structure, we can idealize this one to be like this. We have a concrete slab which is reinforced in two directions poured in on plane forms. So normally in this diagram you can see the force will be transferred in one direction only. But take note that is for one-way slab action, which requires that the ratio between the slabs L2 and L1, L2 over L1 should be greater than 2. But if the ratio between this length L2 and L1 is less than 2, then the action will become two-way action, meaning the forces will be transferred in one direction and in the other direction, which is perpendicular to it. So we call it two-way action, and normally the slab will become two-way slab. So here we have the two-way system. According to ACI 318, ACI means American Concrete Institute, and ACI 318 is the building code requirements for reinforced concrete. If the length L2 of the span should be greater than L1, and the support ratio, that is L1, L2 over L1, is less than or equal to 2, then the load is assumed to be transferred to the supporting beams and girders in two directions. So in this case, the slab is, we call it two-way slabs. As the load on the slab intensifies, experiments have shown that 45 degrees cracks form at the corner of the slab, assuming that we have a perpendicular beam. So the result will be 45 degrees. It will crack here. So as a result, the tributary area is constructed using diagonal 45 degrees lines as shown. Even if it's not 90 degrees, normally you just have to take the bisection or the bisection line of the two beams. In particular, this is 90 degrees, so you will just take 45 degrees and 45 degrees on the other side, so you will see a triangle with the height of 5 because this is 10 feet divided by 2, this is 5. And to determine the loading, which is triangular, we simply multiply the uniformly distributed load 100 pounds per square foot by the height of the triangle. Then divide it by 2 because to determine the total force applied in the particular triangle. So here, to determine the height of the triangle, 100 pounds per square foot times 5 feet. So that's 500 pounds per foot. And with the corresponding length of the beam AB, that is 10 feet. Here, if the length L2 is greater than L1 and the support ratio L1 over L2 is equal to 1.5, which is less than 2, then it is necessary to construct 45 degrees lines that intersect as shown in the figure below. So we have a slab beam system uh, with the length 15 feet and 10 feet. So 15 divided by 10, that's 1.5, so it's less than 2. So this is a two-way slab or two-way action. So the forces applied are transferred in two directions, in the short direction and the long direction. To determine the tributary area and the loading, we will just cut the two intersected beams at the middle. Since this is 90 degrees, so it should be 45 degrees. 45 here, 45, 45. Yan. So for the beam AB, the load to be supported by beam AB is this shaded portion, the trapezoid. So you will expect that the idealized loading for this beam is also a trapezoid with the height uh, the uniform load times the height of the trapezoid, that is 5 feet. So 100 times 5, that's 500 pounds per foot here. And so with the distances, here we have 5 feet because this is 5 and 5, here 5, then this is also 5. Then the remaining distance is 5. So we have 5 feet, 5 feet, 5 feet. Aside from that, the beam AC, by the way, beam AB and beam CD would have the same loading. For beam AC and BD, they should have the same loading, a triangular loading. So we have for beam AC, we have to multiply 100 by 5 feet because the height of this triangle is also 5 feet. So that's 500 pounds per foot. And this is the idealized beam loading for beam AC and BD. Of course, if in doubt, you have to consider several models. The ability to reduce an actual structure to an idealized form, as shown by the above examples, of course, can only be gained by experience. So remember that one. In engineering practice, if it becomes doubtful as to how to model a structure, as if you are really doubtful on how to model a structure or transfer the loads to the members, then it is best to consider several idealized structures and loading, and then design the actual structure so that it can resist the loadings in all the idealized models. Anyway, this is only true for the newbies, or even if to the experts, if they are not used to the structure, then they will become also a newbie. But as soon as you will gain experience in modeling, it would be easy for you to recognize what would be the possible idealized structure and loading for a particular structural system. Here is an example from Heveler. The floor of a classroom is to be supported by the bar joists as shown. Its joist, of course, is 15 feet long and they are spaced 2.5 feet on centers. The floor itself is to be made from a lightweight concrete that is 8 pounds per square foot per ends. The slab is around 4 inches thick. Neglect the weight of the joist and the corrugated metal deck and determine the load that acts along its joist. Sorry for that. The example is in English units. I was not able to convert it to SI units. Anyway, it's good, or it will be advantageous on your side if you will learn both system of units. Here is the solution. The dead load on the floor is due to the weight of the concrete slab. Take note, for the lightweight plain concrete, it is 8 pounds per square foot per ends. And since we have 4 inches thick slab, we just have to multiply it by 8. So 4 inches times 8 pounds per foot square per end, so that would become 32 pounds per square foot. The live load for a classroom is in SI units, that's 1.9 kilopascal, which is equivalent to 40 pounds per square inch. Thus, the total floor load is equal to the plain concrete and the live load. That's 32 pounds per square foot plus 40 pounds per square foot, which is equal to 72 pounds per square foot. Remember, in adding the dead load and the live load here, we just assume that we don't have to multiply load factors. So this can be used for the service load. For the floor systems, L1 is equal to 2.5 feet and L2 is 15 feet. Since L2 over L1 is greater than 2, then the concrete slab is treated as a one-way slab, meaning the forces will be transferred in one direction, that is in the short direction. The tributary area for each joist can be shown on the right diagram. That is 2.5 feet as the tributary width times the length, which is 15 feet. Thus, the uniform load acting along its length is equal to 72 pounds per square foot times the tributary width of 2.5 feet. So W will become 180 pounds per foot. Another example is the flat roof of the steel frame building shown in the photo. This is a realistic photo, so that it will really help you idealize structures in the future. This is intended to support a total load of 2 kilonewton per meter square over its surface. You determine the roof load within the region here, A, B, C, D, that is transmitted to beams BC and DC. As you can see, here are the dimensions and how we draw the tributary areas. For this particular section ABCD, we have drawn a 45-degree angle here, 45, 45, 45, and then you can draw a line that connects the intersection between the 45 degrees line here, so that the shaded portion number 1, which is a trapezoid, and a shaded portion 2, which is also a trapezoid. The loading coming from 1 and 2 will be carried by beam BC. But of course, in our example, because it says A, B, C, D only, so the force to be carried by BC in our example will be coming from shaded portion 1. For beam CD, the force to be carried is taken from the shaded portion 3, which is triangular. So here is the solution. Since L2 is 7 meters and L1 is 4 meters, by taking the ratio between L2 and L1, that's 1.75, which is less than 2. So we can conclude that this is a two-way slab action, meaning the forces will be transferred in the short direction and in the long direction. The tributary loading along its beam is shown in this figure, or the earlier figure, where the lighted shaded trapezoidal area 1 is of loading is transmitted to beam BC, and the peak intensity of this loading is simply equal to the loading 2 kilonewton per meter square times the tributary width of 2 meters here. So 2 times 2 is 4 kilonewton per meter. So we have a trapezoidal loading 4 kilonewton per meter. Again, I want to emphasize this is only for the shaded portion 1. But in reality, if you are designing, you need to include the tributary area 2 to be added to 1. So you have to multiply it by 2, so it will become 8 kilonewton per meter. The process of the tributary load transmission should also be calculated for area 2 to the right of BC. And this should also be placed on BC. Okay, and also a triangular distributed loading on the area 3, which acts on a member DC. It also has a maximum intensity of 2 kilonewton per meter square times the height of the tributary area, 2 meters. So this will give us a loading of 4 kilonewton per meter, which is a triangular loading for beam. So okay, that's all for the modeling of structures, and I hope you are ready now for uh, the succeeding lectures on how to analyze structures. Thank you for listening.